Alright, welcome back. Now we're talking about functions in section 1.4. Our objective is going to be to review functions, evaluate piecewise functions, determine the domain of a function, simplify different quotients, I bet you remember that a little bit, and then solve word problems involving functions. I'm going to admit here that I'm going to take a little bit of a shorter version of this video than it could be, mostly because functions and stuff is stuff you've been talking about since Algebra 1, so I don't want to beat you to death with something that you already know. I'll let you basically ask questions in class for the things that you don't remember. So basically those things that I would expect you to kind of remember, or at least pretty well, is domain versus range of a function, how to tell if something, being an equation, ordered pairs, or a graph is a function, and then general function notation. Any questions on that, definitely hit me in class with those. Otherwise, let's not waste time going 20 minutes over something that you learned in Algebra 1 if you don't need to hear it. Okay, now one issue that sometimes people have with evaluating piecewise functions is knowing where to plug it in, or do you plug it into all of the different pieces or whatever. So a piecewise function is exactly what it sounds like. It's a function defined in pieces, usually designated by some inequalities over here on the right hand side. So the function is 3x minus 7 if the x is less than or equal to 4, but it's x squared plus 5 if x is greater than 4. So if you have to evaluate the function at various points, well, for f of negative 2, okay, well, you just kind of look at the inequalities and decide where negative 2 falls. Well, negative 2, of course, falls less than 4, so we're going to use the corresponding part of the pieces of the function. So you'd plug the negative 2 into that top half because that's the inequality that corresponds to that particular x value, and then you just work that out. So we get negative 6 minus 7 gives us negative 13. Alright, of course, then if you have f of 4, okay, well, now to be a function, of course, I can't have 4 defined in both. So notice how one of these has the or equal to bar and the other one doesn't. If I had both or equal to bars, then actually I don't have a function anymore, or at least it's unlikely. So you'll never see that. So anyway, since the 4 is in the or equal to, again, we would still plug into the top half. So simply 3 times 4 minus 7, which is better known as 12 minus 7, or even better known as simply 5. Alright, moving on to our last one, f of 6. Well, no shocker, since I've used the first guy twice, and I have a second one that I haven't used yet. Probably that's where he's going to fall, and of course, because 6 is greater than 4, sure enough, we plug it in there. So instead of x, I plug in the 6, I get a squared plus 5, and then of course it's 36 plus 5, which most days of the week works out to be 41. So that's how you handle the piecewise functions. Please don't plug it into both, just plug it into the one that it matters for. Okay, let's talk about the domain of a function for a little bit here. Alright, of course the domain is the x values that are defined by the function. Okay, and there's only two bad things that can happen when we're talking about domain. Okay, first of all, you can't divide by, well, what number can't you divide by? Hopefully you were thinking about that before I actually wrote it in there. You can't divide by 0. Basically what that means more in a more practical sense is whatever, if we have a function, our denominator can't be equal to 0. So we can work with that to figure out any bad domain values that are out there. Secondly, you can't take an even root of a negative number. Pardon my shorthand right there. And what that's going to work out to be for us domain-wise is that the radicand, big fancy word right there, which really just means, remember, the number under the radical. The radicand, if you have an even root. If it's an odd root, we don't care, but as long as you have an even root, the radicand has got to be greater than or equal to 0. Okay, and this will find us our good values. Now, one important distinction here is when we're talking about the denominator not equal to 0, what we're finding is the bad values that we have to throw out. When we do this, the radicand greater than or equal to 0, what we're doing is finding the good values. Okay, moving on real quickly to an example right here. Now, this one you might be thinking, what? But basically here, the function is this, and what you want to ask yourself is, do I have any of these bad things happening? Okay, is there any occasion here where I divide by 0? Well, there's no division at all in this problem. If I were to start plugging in values, so, well, can't divide by 0 because there's no division. And also there's no even roots. Okay, there's an even power. Please don't confuse roots versus powers. I got an even power, but again, I'm not trying to take a root anywhere, so I'll never have to take the root of a negative, so again, I don't have to worry about that. So basically there, my domain, if I'm worried about that, is going to be all reals. Okay, so we can use that, simply say all reals, just write all the words out, or if you're talking interval notation, of course you can just simply say from negative infinity up to positive infinity. So basically, the little symbol for all reals, you can simply write the word all reals, or even all real numbers if you prefer a little bit more wordy of an answer, or just again, the negative infinity to positive infinity interval notation version of that answer. Okay, we've got a little interesting, or a little more interesting scenario here, in that now I've got a denominator, so I do have some division going on, so I do have to worry about whether or not I have a 0 in the denominator. So again, what I said before is if I've got this, what I need to worry about is any place where my denominator is going to be equal to 0, and what I like to do, just as my own personal habit, is I throw the not equal to sign in there, because again, this is reminding myself that these are my bad values that I'm finding. Alright, so whatever equation you have, in this case I left myself a quadratic, but you can go ahead and factor this guy, 2x plus 3, 2x minus 3, not equal to 0, and just treat it like it's a regular equal sign, because that's exactly what we're doing here. And so now we've got x is not equal to, again, we've got negative 3 halves, and then positive 3 halves. Again, if you want to go with a plus or minus notation, that's good. But basically what's going on here is our domain is going to be all reals except plus or minus 3 halves. Next example we've got here, we've got another function, and we've got a root. And now remember, anytime you have a square root, there's an understood 2 as the index, so one of those few times in math where something that's missing isn't implied to be a 1. Well anyway, because we have the 2, we have an even root, so I have to worry about whether that radicand is greater than or equal to 0 or not, because again, I can't take the square root of a negative. When we're talking functions, we pretty much skip I, so that's why we're not going to worry about that right now. But anyway, we've got the 8x minus 5, and again, what I want is now that to be greater than or equal to 0. So again, now what I'm doing is finding the good values. Last example, we found the bad ones, so we ruled them out. Here we're going to find the good ones. And we have a very linear situation here, so this one will be very complicated to solve. But adding 5 to both sides gives us this, and then of course dividing through by the 8, we get x is greater than or equal to 5/8. And so again, if that's the notation you're going with, that's great. Again, putting on the big boy math pants that we're currently working with, or big girl math pants, not to be sexist. We've got this in our domain. We can write an interval notation. Again, bracket here, 5/8, going all the way up to infinity, and there you go. So there's our domain for this guy in interval notation. Again, if the other interval notation isn't specified, the other notations would be allowed. But there you go for domain. Okay, we mentioned difference quotients before, and this is just another time we're going to kind of rear their heads, because we are talking about function, and this is very function driven. And like I said when we did these a little bit ago, these are used in calculus, and I'm going to continue to let them haunt you until we actually get to calculus and use them in the exact way that they're meant to be used, but we'll get there when we get there. Alright, so anyway, I've got my function right here, and I want to kind of work out this. Again, it's called a difference quotient. And so again, it's just really some function notation. You're just really doing a substitution and then simplifying the mess that comes out of it. Alright, so I want f of 2 plus h, so again I'm plugging in into my original function. Everywhere I see an x, I'll put in a 2 plus h. Now I've got this to the third power, minus 5. And then of course, minus the f of 2. I'm going to throw that in parentheses just to not make any sign mistakes here. So I've got my 2 to the third, and then minus 5, closed up in a parenthesis there, and that whole thing's going to be divided by h, because that's what it says to do right there. Alright, I kind of do this one mostly because if you have to take something to the third power, a binomial like this, well, we can go write this thing out 3 times and then do FOIL for the next 5 minutes, give or take. But what I'm kind of doing this for is to maybe remind you of kind of the binomial theorem, a way of taking binomials to powers. It involves some Pascal's triangle kind of stuff. If that means nothing to you, then please ask me in class. But basically what we have here is a coefficient of 1 for the first term being cubed, plus 3 times the first guy now down to the second power, and then the second guy, now he's up to the first power. Notice there was a 0 of him the first time. And then the 3 repeats itself. Again, it's a Pascal's triangle sort of thing. Alright, now that 2, he's down to the first power, and then the h, he's up to the second power, and then my coefficient now is 1. Now the h is up to the third power, and the 2 has disappeared. So that's this guy cubed written out in a, well, hopefully a quicker way of doing it than foiling for a whole bunch. Still got that minus 5 on there, I don't want to lose track of him. And then if you permit me to do so, 2 to the third is 8, so minus 8, and then the minus 5 right there. Alright, again, that whole mess is over in H, and right now it looks like a big hairy mess, and it kind of is, but it's going to sort itself out a little bit here in just a minute. Okay, 2 to the third is 8, and the 1 doesn't change anything. Okay, I've got 2 squared here, which of course is 4 times 3, gives me a 12h. And then this will be a 6 with an h squared on it. And then I've got this h to the third. And then I've got a minus 5, and then this is going to be minus the 8 minus 5 is a 3. So minus 5 minus 3. And again, all over h. Good news about all those numbers without h's on them, 8 minus 5 minus 3, those all cancel themselves out. And then if you permit me, this h will reduce with the other 3 terms, because they all have an h in them. And so, well, without changing the order here, I'll have 12 plus 6h plus h squared. Okay, if we wanted to, we could rewrite that in descending order, but based on the way the original problem was written, and kind of an ascending order sort of thing, I'm going to leave my answer in that format as well. Okay, now this difference quotient is kind of the more traditional ones, or at least from my point of view, because these are the ones that we're going to do in calculus a little more often. Where the x's are there. The last one we used a number instead of x, and it gave us some kind of things that worked themselves out a little bit, but calculus-based ones, we're going to do the variable-laden version of it instead of the number-laden version a little bit more. So just to hit you with one of those again, if you feel comfortable with this, feel free to fast forward through this part, but here we go. Okay, again, f of x plus h, so in my original function, anywhere I scan x, I'm going to put in x plus h, so I got that squared, plus 6 times the x plus h. And now subtracting the original function, so x squared plus 6x. And again, that h is on the bottom. Again, that will be a common trend of these things, and eventually it'll make a lot more sense why that's in h all the time, but just for now, hey, that's how it works. Okay, squaring out the x plus h gives us an x squared plus 2xh plus h squared. And then distributing the 6, and subtracting x squared, and now distributing that negative sign gives us a minus 6x. And again, still all over h. And just like the last problem, you do have a lot of stuff that kind of cancel this stuff out. Basically, everything without an h on it goes away, and that's not a coincidence. And then again, if you permit me to be a little bit lazy here, I can reduce things by h from there. So I've got a 2x, the h reduces down, or h squared reduces to an h, and then the 6h reduces just down to a 6. And so again, that big hairy mess turns into something that's not too bad. And I don't normally do this with the videos, but here's the assignment. I'll put it in the video, especially if you're one of the folks who's printing these things out. Well, now you have the assignment staring in the face already. A little something different right here. It'll be enough to understand thing. A lot of this is the review of some of the function notation that honestly stuff you've been doing from Algebra 1. Like, is it a function? You know, evaluate f of 7 for this polynomial or things like that. So I don't think you need to do all of those by any stretch of the imagination, but I'm sure some people need to do more than others, so basically I'll leave it to you to do as much as you need. And then here's some other specific ones that I want you to do that are a little more challenging. A couple of those are word problems, so please focus on that and do what you need to do to make sure that you understand it. Thanks much. Have a good night.